In this video, we're going to go over a series of properties of solutions that are called colligative properties. You are going to need a notebook, you're going to need something to write with, and once you have those things ready, let's go. Okay, so I'll start off with an example that you guys are kind of familiar with since we live up in the Northeast, and that is the idea of salting the roads in winter, right? So before any large winter storm hits, what you'll see is, for example, the town DPW pouring rock salt or calcium chloride on the roads to prevent the roads from becoming icy. Now, the reason why they do this isn't that the salt will melt the ice, but what happens is that the salt that they put down will actually lower the freezing point of water enough to keep it from freezing. So it's not that the ice is frozen and then it melts. It's that as it dissolves, it keeps the water that's falling as precipitation from freezing on the ground. So this is an example of a colligative property. A colligative property is any property of a solution or mixture that will change its value based on the concentration of what's dissolved. So for example, for our salt on the road, the more salt you put down, the higher the concentration of salt, the lower the freezing point of the water will get. So it'll keep it from freezing at lower temperatures. Alright, so we are going to cover a handful of these. We're actually going to cover freezing point, we're going to cover boiling point, we're going to talk about vapor pressure, and then a little bit into osmosis. Alright, so we'll start off with freezing point depression. So for freezing point depression, like I was just saying kind of in the last slide, the more concentrated a solution is, the lower its freezing point is going to be. Regular distilled water freezes at 0 degrees Celsius. Solutions containing water will freeze at lower than 0 degrees Celsius. And the exact equation that we have here is that the change in freezing point, so delta TF, is equal to KF, which is a constant that's based on the solvent. You'll get that whenever you need to do a problem with it, times the molality. Molality, remember, is moles per kilogram, right? We did molarity earlier on in the year, and we've been working with that consistently, which is moles per liter. Molality is moles per kilogram. And then we're going to multiply that by what's called the Van 't Hoff factor, which is I. I'm going to cover what that kind of is on the next slide, but Kf times m times I, if you multiply those things out, it will tell you how much the freezing point will change by, and then you can just subtract that number from the freezing point of the pure liquid to figure out what the freezing point of the solution is. Alright, so here's how the Van 't Hoff factor works. It's basically just the number of pieces a solid will dissolve or dissociate into when you form a solution. If the solute is a molecular solids do not break up when you put them in water into ions. So for molecular solids, the Van 't Hoff factor, I, is equal to 1 because it's still just one piece. But when you start getting into ionic solids, you add up the total number of ions in the sample, right? So sodium chloride, when it dissolves, breaks up into a sodium ion and a chloride ion. So I is equal to 2 because you have two different ions. Calcium chloride breaks up into a calcium 2 plus ion and 2 chloride ions for a total of 3. So one of the things that we can actually tell just by looking at this is that if I have the same molarity of sodium chloride versus calcium chloride, the calcium chloride is actually going to affect the freezing point of water more than sodium chloride is. That's why they use rock salt or calcium chloride on the roads in the winter, because it has a larger effect on the freezing point of water, so you can get more of an effect by using a lower concentration. Now, similarly to freezing point, we can also talk about boiling point, right? So same thing, if you increase the concentration of a solution, the boiling point of the solution will increase. And it's a similar equation to what you get from freezing point. Change in boiling point is equal to Kb, which is the boiling point constant, times the molality times I. An example that you see of this is that if any of you have ever done any work on cars or anything, you may be familiar with coolant or antifreeze. Antifreeze is a mixture of water, and old antifreezes were ethylene glycol. Nowadays they use proprietary substances. But the idea is that if you have that solution of the antifreeze mixture, in this case we'll say ethylene glycol, that will raise the boiling point of the water by enough to prevent the water from boiling inside the car. That way the engine can actually move the fluid through and keep it kind of cool. Another example of a colligative property is what's called vapor pressure reduction. Right? We just went over in the previous slide what vapor pressure is, right? It's just the pressure generated by the gaseous particles that have managed to evaporate. Well, if we have a solution, the vapor pressure of a solution decreases as the concentration goes up. The reason why is because those solute particles block the solvent's ability to escape from the surface, right? You're kind of plugging in those holes, and when you don't have those holes, the solvent can't get up, even if it has enough kinetic energy normally. So the only way to get it up and out is to give it more kinetic energy, right? So it needs to be at a higher temperature to produce the same vapor pressure. Again, the positive side of this is why we get boiling point elevation, right? Because the boiling point is where the vapor pressure equals the atmospheric pressure. Since you need a higher temperature to get the same vapor pressure because of all the solute particles in the way, the temperature needs to be higher in order for the substance to boil. Okay, so that is vapor pressure. We'll just cover very quickly osmosis, right? So you covered osmosis probably a little bit last year in bio, but the thing to keep in mind for osmosis is that if you have two solutions placed on opposite sides of a semi-permeable membrane, remember, semi-permeable just means that it will allow certain particles through and certain particles not, and those two solutions are at different concentrations, what's going to happen is that water will pass from the diluted solution into the more concentrated solution until both concentrations are the same, right? So it'll go from the dilute solution. As it leaves that solution, the dilute solution gets more concentrated. It'll enter the more concentrated solution, which dilutes it, bringing its concentration down. And then when those concentrations are at the same value, the solution reaches equilibrium, right? So that's what osmosis is. So the thing to keep in mind, solvent molecules will always travel from low concentration to high concentration. So what we have here in the diagram is we have two solutions. The blue solution is the lower concentration. The red solution is the higher. If we let some time pass, it will pass through the semi-permeable membrane. And notice the volume of the blue solution drops as it becomes more concentrated, and the volume of the red solution increases as it becomes more dilute, until eventually they wind up reaching the same concentration and equilibrium. Now, osmosis can have some effect on living tissues, right? So the idea is that if we compare the concentrations inside of a cell and outside of a cell, if the concentration of a solute is higher inside the cell is what's called hypotonic, and what it's going to do is it's going to absorb water from the surroundings and start to swell up and get bigger. If the concentration is lower than that of the surroundings, it is hypertonic, and it will shrink as it gives off water to the outside. And if the concentrations of the solute are equal to that of the surroundings, then it's isotonic, and that means there's going to be no net movement. So one of the important things if you're going into a medical field is whenever you make an IV solution that goes inside of a patient, you generally want to make that IV solution to be isotonic. You want it to have the same concentration of ions as that person has in their blood and in their cells, so that you don't cause their cells to swell up and burst or shrink, wither, and die. And as an example of this, some of you may have seen this last year in biology depending on who you have, but we can use a gummy bear as a perfect example of our cell membranes. Right, so in the upper right-hand corner, we have the original unmodified gummy bear. If we put that gummy bear in salt solution, gummy bears have a little bit of salt to make them actually have a taste, right, but not a lot. But if we put them in salt solution, the salt solution is more concentrated than the salt in the gummy bear, so what's going to happen is that the water will leach out of the gummy bear into the solution, causing the bear to shrink. If we have sugar water or corn syrup-based water, anything that has sugar basically, the concentration of sugar in the gummy bear is obviously much higher than that in the solution because the gummy bear is almost entirely sugar, right? So what's going to happen? water is going to come rushing in until the concentration of sugar inside is the same as outside. The bear gets bigger. Now, if we put in pure water instead, you see how the gummy bears become massive. The reason for this is that water has no concentration of any of those ions in solution, so it's going to try its best to filter into the gummy bear to make it as large as possible, to dilute those concentrations as much as it can without kind of bursting the gummy bear. Although if you leave it sit for a couple of hours, you'll see the gummy bear will actually start to kind of swell up and then dissolve in the solution because of the very large difference between the concentrations of sugar and salt in the gummy bear and the nothing that you have outside. Okay, so those are colligative properties. In the next video, what we're going to start talking about is we're going to start talking about solids. So we'll go over the 4 different types of solids. And then our last video, we're going to start talking about mixtures of solids, which are alloys.